Welcome to lecture 6.1 on the systems of equations in two variables. Today we're going to learn about solving a system of two linear equations in two variables by graphing. We're also going to solve a system of two linear equations in two variables using the substitution method. We're going to learn about the elimination method, and then we're going to use systems of linear equations to solve applied problems. A system of equations is composed of two or more equations considered simultaneously or together. For example, 5x minus y equals 5 is just a linear equation. But if we combine it with another equation, 4x minus y equals 3, now we have a system of equations, just more than one. This is a system of two linear equations with two variables, the variables x and y. The solution set of this system consists of all ordered pairs, x, y coordinates, that make both equations true. The ordered pair 2, 5 is a solution of this system. If you plug in x equals 2 and y equals 5 into both of those equations, you'll see that they are both true equations, or both values make both equations true. When we graph a system of linear equations, each point at which the graphs intersect is a solution of both equations, and therefore a solution of the system of equations. So let's solve the previous system that we just looked at by graphing each line on the same graph. And here you can see that graph, and you can see where they intersect right at 2, 5. We can see that the graph intersects at the single point, 2, 5, and so this is the solution of the system of equations. So when you have a system of linear equations, wherever they intersect, those are the solutions. If a system of equations has at least one solution, it is consistent. This is vocabulary for you. Consistent. A consistent system has at least one solution. If a system has no solutions, it is inconsistent. Inconsistent, no solutions. If a system of two linear equations and two variables has an infinite number of solutions, we say the equations are dependent. And really what this means is they're actually the same line. They're right on top of each other, but they may not look it. Maybe they're a multiple or etc. Otherwise, they are independent. Okay? So if they're the same line, they're dependent because they're really the same thing, and otherwise they're two independent or very different graphs. So let's look at some examples here, and this may help you with some of that vocabulary. In this first example, we can see that there is one common point or intersection where they cross. There is one solution. This therefore is a consistent system. And they are independent because they are two different lines. Two different lines, and they're consistent because they have a solution. Second one, we have two parallel lines. Parallel lines by definition have no common points, and because there's no intersection, there is no solution. So this system is inconsistent because there's no solution, but it's still independent because they are two different lines. They're not the same line. Here, you can't really see it, but there's actually two lines here. The green line is behind the purple line. And here we have the lines are identical. They're overlapping. So any point that's on one line is automatically on the other. And that's why we say there are infinite number of solutions, because there are infinite number of points along the line. And again, so if a point is on one line, since they're the same line, it's on the other. So again, this is consistent because it has at least one solution. In this case, it has infinite solutions. But in this case, it's dependent because they are not independent. They're not two different lines. They're really just the same line. So independent means they're two different lines. Dependent means they're technically the same line. Consistent means there's a solution, at least one, and inconsistent means there are no solutions, or the lines are parallel. The substitution method is a technique that gives accurate results in solving systems of equations. It is most often used when a variable is alone on one side of an equation, or when it is easy to solve for one variable. Here we can see that y equals 3x plus 2. The y is alone by itself, so we could substitute this formula for y into another equation. One equation is used to express one variable in terms of the other, then it is substituted into the other equation. So let's try this. Use substitution to solve the system. 5x minus y equals 5 and 4x minus y equals 3. So we're trying to find a solution which is an x and y value that will solve both of these equations. When we're doing substitution, the first thing we're going to do is to solve one equation for one variable. That simply means we're going to rewrite the equation as x equals a formula or y equals a formula. In these equations, it's easier to use y because y doesn't have a number in front of it, but it has basically the coefficient of 1, so we can solve that. So I'm going to solve this first equation for y. I'm going to add y to both sides, and so I'm going to get 5x equals 5 plus y, and then subtract the 5 from both sides. And so I get y equals 5x minus 5, and that's just rewriting this first equation, solving for y. So that's the first step in substitution, is to solve one of the equations, and we could have solved the other, it doesn't matter, for one variable. And that's just rewriting as x equals a formula or y equals a formula. The second step is we're going to substitute this equation, the formula from step 1, into the other equation. And this is really important that you use the other equation. So we have 4x minus y equals 3. Well, we have a formula for y, so we're going to substitute in the formula for y. So where we had 4x minus y, we're going to have 4x minus, and when you're substituting in formulas, use parentheses. 4x minus parenthesis 5x minus 5 parenthesis equals 3. Notice all we've done here is substitute in the formula for y for the variable y. Now we simply solve this. Minus a 5x minus a minus 5 is plus 5. And if we do the algebra here, we get x equals 2. The last step is to plug the answer from step 2 back into the formula found in step 1. And that way we'll know what y equals as well. So from step 1, we had y equals 5x minus 5. We know that x equals 2. So we plug in 2 for x, and we get 5 times 2 minus 5, or simply y equals 5. So the solution is the ordered pair 2, 5, as we saw on the graph in the previous problem. Elimination method. Using the elimination method, we eliminate one variable by adding the two equations. If the coefficients of a variable are opposites, as you can see down here, notice the numbers in front of x are opposites, 2 and negative 2. That variable can be eliminated by simply adding the original equations. It's important that you line up the equations, that they're in standard form, x plus y equals constant or x minus y equals constant, so that you're adding all the like terms, okay? So notice if we add these two equations together, we get 0x plus 6y equals 12. Well, 0x just goes away, and we get y equals 2. We could then plug this into either equation and figure out what x equals. It's very simple, okay? These can be more complicated. If the coefficients are not opposites, it is necessary to multiply one or both equations by suitable constants before we add, so the coefficients are opposites. So using this same equation, assuming we wanted to get rid of the y coefficient, the y variable, notice if we multiplied the second equation by negative 5, then we'd have plus 5y and minus 5y. So let's try that. Now this means that we multiply both sides of the equation by negative 5. That means we multiply every single thing on both sides by negative 5 and do distribution. When we do that, we get 10x, positive 10x, minus 5y equals negative 10. We can bring back the original first equation, and now notice when we add these together, the y's disappear, it's eliminated, hence the name of this method, and we get 12x equals 0, or simply x equals 0. So why don't you go ahead and try to solve this solution, solve this system. It's a little bit more complicated, and try to get rid of the x variables. What would you multiply? In this case, we're going to have to multiply both equations by something in order to get opposite numbers in front of the x. Notice if we multiply the first equation by 5 and the second equation by -3, we will be able to eliminate the x variable. You might think of these as denominators, okay? And you're looking for the least common denominator. What number do 6 and 10 both go into? One way that you can do this is take the larger number and just do multiples. 6 doesn't go evenly into 10, so 2 times 10 is 20. 6 doesn't go evenly into 20, so let's do it again. 3 times 10, oh yeah, okay, is 30, and 6 does go into 30, okay? So you can find a common denominator by simply using the large number and keep doing multiples until the smaller number goes into it. So 6 times 5 is 30, and 10 times 3 is 30. But again, since they're both positive, one of these numbers has to be negative, or the opposite sign. So we're going to do 5 times the first equation and -3 times the second equation. And this gives us 30x plus 10y equals 20 for the first equation, and -30x minus 21y equals positive 24. Now these we can solve by simply adding them. I'm not going to go through this very much, but if we add them, we get -11y equals 44, y equals -4. We would then take that and substitute into either one of these original equations. We're going to use the first one. Where we have y, we're now going to substitute -4 and then solve for x. And so we get that our solution is 2, -4. Remember, our solution is an ordered pair, an xy coordinate on the grid, which represents where the two lines would intersect. So let's solve another system. Okay, here we have x minus 3y equals -9. 2x minus 6y equals 3. Well, if I want to get rid of the x's, what I'm going to do is I'm going to multiply the first equation by -2, okay, because I have a positive 2 here and a 1 there. So if I multiply the first equation by -2, I can now add the second equation to it and get rid of the x variables. But something weird happens here, and that is that I also got rid of the y variables. And that's a bit of a problem, okay? When the variables disappear and what is left is false, as you can see here, 0 equals 21, that's not a true equation or statement, equality. When the variables disappear and the equation is false, then we know that we have no solution. There are no values of x and y in which 0 equals 21, so this system has no solution. Well, what do we know? If there are two lines and they have no solutions, solutions are where they intersect, so they don't intersect, so these two lines actually have to be parallel. Let's try another. See if you can figure out how to solve this one using elimination. We have 9x plus 6y equals 48. If we multiply the second equation by -3, we can get rid of the x variables. -9x minus 6y equals -48. And when we add this, we have a problem again because all of our variables disappear. Okay? When all the variables disappear, but the equation is true, then there are many solutions because this is the case where they're the same line. This is the dependent system where they're actually the same line. notice if you divided the first equation by 3 on both sides, you would get the second equation. So they're just multiples of each other. When we obtain the equation 0 equals 0, we know the equations are dependent. There are infinitely many solutions. The graphs of the equations are identical. So let's look at some problems now. Ethan and Ian are twins. They have decided to save all the money they earn at their part-time jobs to buy a car to share at college. One week, Ethan worked 8 hours and Ian worked 14 hours. Together, they earned $256. The next week, Ethan worked 12 hours and Ian worked 16 hours, and they earned $324. How much does each twin make per hour? Well, one of the first things you want to do with these problems is look at the question. Remember that the question creates your variables. How much does each twin make per hour? And it's a good idea to do like I've done here, to use the variables that are connected to the problem. So instead of using X and Y, I'm going to use E to represent how much money Ethan makes, and I'm going to use I to represent how much money Ian makes. This helps you solve the problem because it helps you connect with the context of the problem. Most of the math you do in your life is word problems, but you do them easily because you understand the context already. In word problems in a math class, you need to help yourself connect to the problem with the context. And one of the simplest ways to do that is simply use variables or letters that represent the concepts in an intuitive way by using associated letters. E for Ethan, I for Ian, H for height, S for speed, etc., etc. Now we can use the information given. We know that E is how much Ethan earns, and he worked 8 hours. Ian worked 14 hours, so 8 times E plus 14I equals their combined income. See if you can write the equation for the second week using the next sentence. Hit pause and see if you can do it. So here we have Ethan worked 12 hours, so that's 12E. Ian worked 16 hours, that's 16I, and they earned 325, or equals 324. Now I have a system of equations. I can now solve this. This is a really interesting one that I wanted to show you. They are both even. We could reduce these by dividing everything by 2, and that might make it a little bit simpler. But also one of the things that we can always do, for example, if we want to get rid of the variable E, and we have numbers like this that aren't exact multiples of each other, we can just multiply each equation by the coefficient on the other one. Now what am I saying? So take the 12 from the second equation and multiply it times the first. That's what I'm doing here, or have done here. Take the coefficient on the first equation and multiply that times the second, and that's what I've done here. Except that I added a negative. Now why did I do that? Because right now they're both positives and we need them to be the same number but opposite signs. So one of these has to be negative, and it doesn't matter which one I make it. So notice now that when I add these together, the E disappears and I get 40I equals 480. And so I equals 12, so Ian makes $12 an hour. Now remember, with this elimination, all I have to do is plug this into either equation and I can solve for the other variable. So using the first equation, 8E plus 14I equals 256, and substituting in 12 for I get 8E equals 88 and E equals 11. So our answer is that Ian makes $12 per hour while Ethan makes $11 per hour. Okay, again, a couple of points here is your question is your variables. Use letters that are connected to the problem for your variables, and then go back and build equations based upon the data and stuff given in the problem. With elimination, you can always just juxtapose, take the coefficient from the first and multiply times the second, take the coefficient from the second, multiply times the first, and ensure that, again, the signs are opposites. All right, this one freaks many people out. At Max's Munchies, caramel corn worth $2.50 per pound is mixed with honey roasted mixed nuts worth $7.50 per pound in order to get a 20-pound mixture worth $4.50 per pound. How many pounds of each snack is used? Now this is a lot of data in there and it's confusing to know what to do. So with these kind of mixture problems, I always suggest people build a table, and actually most of these system problems, I suggest you build a table. So we're going to, again, remember what we're looking for. We're looking for pounds of each snack. So we're looking for pounds of caramel corn and pounds of nuts. So that's what I'm going to make my variables. The number of pounds of caramel corn is going to be C. The number of pounds of nuts is going to be N. And the price per pound, caramel corn is $2.50, nuts are $7.50, and we want the final mixture to be worth $4.50. So if I have C pounds of caramel corn, that's worth $2.50 per pound, I simply multiply this, 250 times C, and that gives me the value of the matrix. So we have a price here, the number of pounds, and then the value of it. Okay. Over here we have the mixture, and this is what we're targeting. We want to make 20 pounds of this mixture. And so the value of this mixture at the end will be the 20 pounds times the $4.50 that it's worth, or worth $90. Once we've built the table, we can now find equations, I think, a little bit easier. So if I have C pounds of caramel corn and N pounds of nuts, but totally they add up to 20 pounds, well, that's my first equation. C plus N equals 20, the total amount. The value of the caramel corn is 250 C. The value of the nuts is 750 N. And we know that the value of the mixture at the end is going to be 90. So it's 2.5 C plus 7.5 N equals 90. Now we have a system here, and one of the things that we do in algebra is get rid of fractions, get rid of decimals when we start to solve problems. So notice if I just multiply the second equation, the value equation, by 10, the decimals will disappear, and I can get something that's a little bit easier to work with. 25C plus 75N equals 900. All right. Now this is a relatively easy equation to solve based upon either substitution. We could solve the first one for C equals 20 minus N and plug that in. We could multiply the first equation by negative 25, and that's what I've done here. If I do that and then add the equations together, I get N equals 8. Okay, I'm not going to go through those steps. All I've done here is multiply the first equation by negative 25. And then I'm adding them together and solving for N because the C disappears. Okay. Once I have the amount of N, the easiest thing to do is to plug it back into this first equation. C plus N equals 20. And substituting in N equals 8, I get C equals 12. So this is not as difficult as it seems, these mixture problems. Remember, you're going to do a price, a quantity, and then the value of whatever you're mixing, etc. Typically these tables you multiply down and add across. So our answer to this problem is the mixture should consist of 12 pounds of caramel corn and 8 pounds of honey roasted nuts. All right, this is the problem that everyone hates, and that's why they hate math teachers as well. An airplane flies the 3,000-mile distance from LA to New York with the tailwind in 5 hours. This means the wind is pushing it. Okay. The return trip against the wind, that's a headwind, takes 6 hours. Find the speed of the airplane and the speed of the wind. Again, remember we want our variables to be the question, so we're looking for two speeds. We're looking for P, which is the speed of the plane, and W, which is the speed of the wind. Now, if you've ever rowed a boat in a river or ridden a bicycle in the wind and turned around, you realize that sometimes when you're going with the wind, when you have a tailwind, it's real easy. And when you have a headwind, you're going against it, it's harder and you're going slower. So notice that our speed, the speed the plane is going with the tailwind is the speed of the plane plus the speed of the wind. Whereas when the plane is flying against the wind, it's the speed of the plane minus the speed of the wind. This is another problem that might help you to kind of draw a picture, putting the data on the picture. Here we can see we have speed, time, and distance. These are all just data points from the problem. Taking them out of paragraph form and putting them into a picture, or even better yet, building a table. The distance is going to be the same. Now, this is a key thing. When I see that a column is the same, that's usually a good indicator of how I'm going to solve the problem, because remember, equations have the same thing on both sides, or an equalness, and so this may really help. Well, distance equals rate times time, so I can set these two equations equal to each other, or I can just simply write the two equations based upon my table. Distance equals rate times time. If you forget that formula, and this is a basic formula, you should remember it. You can think of the speed limit sign. Speed equals miles per hour. So it's distance over time. Speed equals distance divided by time. But in this case, we've got distance equals rate times time. So I'm going to make two equations from our table. 3,000 equals 5 times p plus w, and also 3,000 equals p minus w times 6. Notice those are in parentheses so that we distribute. And actually, before we distribute, it might be actually easier to simply divide both sides by that number. So I can divide the first equation by 5 on both sides, the second equation by 6 on both sides. Now, why did I do that? Because notice if this set of equations, this system, already has the variables ready to do elimination, the w's will disappear if I just add those two equations. And if I do that, I get the speed of the plane is 550 miles per hour, and the speed of the wind is 50 miles per hour. I didn't solve this algebraically beyond here, but you should be able to solve that at this point. I wanted you to see that this is the scariest problem to so many people. But when we break it down, and especially again, building a table or building a picture, it really becomes much easier to solve than we realize. Okay, that's the end of 6.1. Hopefully this has been helpful to you, and we'll get you started.